So we can start now, as you want, Andres.
Okay.
Okay.
Sorry, I have to share again because I had an issue with Zoom.
Okay. It's okay. It's okay.
Il faudrait qu'il se fasse beaucoup de présentation.
Pas compris.
You should introduce himself.
Yeah, I told him.
Okay.
We are discussing with François Bachili that you should introduce yourself.
Okay, thanks. And thanks, Francois, for inviting me to this seminar. I was catching up with this latest talk by Carlos, and it was really interesting. I see many familiar faces in the Zoom connection, like Alonso and Daniel. And also I invited my former master's student, Diego Goldstein, to attend. He's now a postdoc at INRIA in Nice with Costa Sarashenkov. So he's a graduate from TUV in Eindhoven. So I invited him to join. I hope that's okay. Okay. So I worked for a long time in stochastic processes, and I'm really a fan of all the PAM theory that Francois taught me like 20 years ago in his course. And recently I found this new application of all the stochastic intensity and PAM theory to an old problem, which is the caching problem that we all know about. So this presentation will be, I'm a professor at the Universidad of Urugay. I'm a PhD from here in Uruguay. I spent some time in France, like 20 years ago, as I said, with Daniel. And now I would like to present our latest results that I'm really excited about how this PAM theory can be used in the context of an old problem, as I said, like the caching and prefetching, and why the hazard rates play a role. So let me begin. This is joint work with Matias Carrasco and Fernando Paganini here in our university. So what's the caching problem? The caching problem is an old problem that we all know about. I mean, we have a local memory or cache. I prefer to call it a local memory system that handles items from a catalog of n objects. And we have a random process of arrivals requesting some items from the cache, but I can only store a small amount of them in the cache locally. If the item is stored in the cache, we have a hit. Otherwise, we have to retrieve it from the central repository or something. We have a miss, and we want to maximize the hit. This problem is as old as computing, of course, but I think that new developments in this field have led to some new interesting results, and in particular performance bounds that are universal in some sense. So the way people think about this problem, or the way computer scientists think about this problem, is what I call a sequential approach. They consider a sequence of random variables with values in the items in the catalog, and they consider this family C is the family of subsets of size less than C, which is possible local memories, possible cache. Okay, so I'm thinking about the sequence of arrivals instead of a point process of arrivals, and we'll get to the point process approach. Okay, so what I want to have a policy that depends only on the past history of requests. So a causal caching policy is a sequence of maps deciding which content to store based on the previous information up to Cn-1. Okay? Or in probabilistic terms, and this will become important, the policy has to be Fn-1 measurable, where Fn is the history of the process. Okay, the filtration of the process. Okay, so I have to be, the policy has to be predictable in order to be feasible. Okay, so the simplest case here is what people in caching call the independent reference model, where we assume that all these random variables are IID with some distribution which is related to the popularity of the objects. And we assume that the popularity is decreasing, so item 1 is the most popular, then 2, 3, and so on. Okay. And if these random variables are IID, then given the past history, Cn is independent, so it has distribution P. Yep. There's a question?
No.
Sorry. Should I go on?
No question. You can go on.
Okay, thanks.
I will check it. Yeah, it's okay.
Okay, so the probability of having a hit is just the probability of the sum of the probabilities of the items that I have in the cache. Okay, so my policy determines what is cache at some point, and this should always be lower than the sum of all the probabilities of the most popular objects. Okay, so what I can do is simply take as a policy, store locally always the most popular objects, and this is optimal under IID requests. Okay, so the static keep the most popular policy is optimal under IID requests. This has been known for a long time. Okay, but of course these popularities are not known, so you have to learn them. So in practice, what is used is some kind of learning process where the most popular is least frequently used action policy, which is just keep account of how many requests you have for an object and use this as an estimator of the popularity of the object and then keep the most popular. Okay, in the long range, this least frequently used policy converges to this static policy. This is good for IID requests, but may not be good for bursty requests when requests are correlated in between them. Okay, the most popular eviction policy in this setting is what is called least frequently used, where you have an object. When you have a request for an object, then either you have a hit or a miss, but this object becomes the most important one. Okay, so you put it at the front of the queue, and at every request, you move this content to the front of the list. Okay, and this is good because it's estimating the popularity of the object, but also adapts best to bursty traffic. Okay, so for bursty traffic, LRU is a very good solution. Okay, the problem is how to model these correlations in between objects, in between requests. This is very difficult. There are many models, and having proper bounds on the probability, the hit probability of LRU is really, really difficult. There are a lot of very interesting papers. There's one by Joaquín Fontbona and Javier Barrera, for instance, from 5 or 6 ago. That's really interesting, and they try to compute the Laplace transform of the steady-state distribution of this process. It's really difficult. Okay, so take 2. The problem with sequential models is that they lack time information, and time information may be useful. So a seminal paper is a paper by Nikes Fofak and Dan Towsley in 2014, when they switched to a point process. Okay, so arrivals are now stationary point process in the real line with some intensity lambda I, which is related to the popularity of the object. So here I have 4 processes. The first 2 are Poisson, so they are mostly homogeneous. This is a simulation. But the other ones, the green and the violet, are bursty because the inter-arrival distribution is chosen so that the traffic is burst. Okay, and what I have to do is the same as before. At each point in time, decide what I have to cache or store in the local. And if inter-request times are heavy-tailed, like the green one, there are long pauses, then I see bursts of requests. So this is a nice way to model the correlation between requests and the burstiness of the request using time information instead of sequential information. But the problem is now that we're in continuous time, and in continuous time it's more difficult to work with. This is another example. Poisson is homogeneous, heavy tail arrival with Pareto alpha equal to 2. You get bursty traffic. Okay, the popularities are the same in both objects, but the pattern is different. This is what I want to highlight. Okay, so these are the questions I want to answer today. What is the optimal policy in this framework? And can we compute something about it? What is its large-scale behavior, and how typical policies like LRU compare to this optimal policy? Okay. So in order to do this, I had to review some stuff about point processes and stochastic intensity. So this is what Francois taught me 20 years ago. A point process, a stationary point process, is just a sequence of times or points in the real line, or we can think about it as a counting measure defined on the real line, which is random with some distribution, okay? And sometimes it's better to work with a sequence of points. Sometimes it's better to work with a measure. That's the interesting thing about this, okay? And we can also define the counting process, which, since I'm working in a steady state, I will define it for all times, real times, okay? So the value is just 0 at 0, that's the idea. And then I count from 0 onwards towards a positive real line, and from 0 downwards towards the negative real line, okay? And I'm abusing a bit here the notation and saying phi of t is the counting process, okay? So we can define the history of this process as the sigma algebra of the information up to time t, okay? The filtration generated by this sigma algebra. This is the history of this point process. And this is what I have available in order to make decisions at some point, okay? And another thing that maybe everybody knows, but it's worth remembering, is that we have two main ways of looking at a point process. We can look at a point process synchronized with the process, which is the bound probability of the point process conditioning at a point, or the steady state, or sampling the point process at a given point in time. So the distribution between 2 points, if I synchronize with the process, has some interarrival distribution f0 with mean 1 over lambda, where lambda is the intensity of the point process. But the age distribution, the time since the last arrival, follows a different distribution here, okay? Which is a well-known Feller paradox, the way you want to call it. But there is a different distribution here than when I look at, as I sample the point process at some point in time, which is not synchronized with the process, okay? And these distributions are worth remembering. Another notion that is important here is what I call the stochastic intensity. The stochastic intensity is a local measure of the intensity of the point process. The formal definition is that we have some function, some random process, lambda of t, that can give me the expectation of the number of points in some interval, given the previous history, as an integral of this random process, given the previous history and taking expectation, okay? And this definition is very mathematical and non-constructive, okay? It depends on the history, but it's very interesting to see what happens. It's very interesting to see what happens locally. The local interpretation is that the number of points in an interval near the time t in a small interval is proportional to the stochastic intensity given the previous history, okay? So this is a local notion of intensity. It's not the average intensity or popularity of the request. It's just the local notion of intensity based on the history. There's also a martingale interpretation. I don't want to get into this. This was here for completeness, but it's also the martingale compensator of the counting process, okay? And by using that this is the martingale compensator of the Poisson process, one can show that the stochastic intensity of a Poisson process is just constant lambda. Okay, so this is generalizing the notion of local intensity of a Poisson process to stochastic intensity. Okay, so the Poisson process has a constant stochastic intensity, and this means that the Poisson process is the white noise of point processes. Okay, we don't have any local information. What may happen at some point in time is the same at every point in time. This is the pure randomness property of the Poisson process, okay? So I think of as the Poisson process as white noise, no information, okay? But if traffic is bursty, the stochastic intensity is not constant. On average, it will coincide with the stochastic intensity, with the average intensity of the process. The near arrivals, the stochastic, if the traffic is bursty, for instance, the stochastic intensity will rise. And why will it rise? Because it's bursting. It becomes more probable to have some new arrivals. Okay? So on average, this process lambda in red, which is random, it depends on the points. Okay, on average, it will be the green line, the average intensity, but acts as a local notion of intensity. Is this clear? Because all the rest of the presentation relies on this slide. So no questions so far?
No, you can go on.
Okay. So let me now consider renewal processes, and this is important. And in the renewal processes, we have the same as before. Phi is point process, but the inter-request times are IID with some distribution F0. And we can define the hazard rate or failure rate, which is well known in reliability theory of the distribution, as the density of the distribution divided by the tail of the distribution. This is a notion of how likely is that some item breaks at time t, given that it has already endured an interval of time t. So in reliability theory, failure of parts or something, this is very well known. Okay, but there is a very nice theorem in the book of Daly and Verjones on point processes. Then if we consider a renewal process and its natural history, then the stochastic intensity of the process is just the hazard rate function since the last arrival, since the last point that we have seen. So for renewal processes, the hazard rate is the stochastic intensity. That's the main point, okay? So if we know the distribution F0, we can somehow compute the stochastic intensity of the point process. If the process is not renewal, this is not true, okay? Because you have more history to take into account. But if it renews at each arrival, then you just only have to consider the the hazard rate of the current interval. So what may happen is that you have constant hazard rate. Constant hazard rate is exponential, is again the Poisson process. So you have constant stochastic intensity. You can have bursty traffic with decreasing hazard rates, but you can also have increasing hazard rates. And increasing hazard rates is very different because it leads to more periodic or regular traffic than the Poisson case. Okay? Because the probability, the likelihood of receiving some request immediately after seeing a request for some object decreases instead of increasing. Okay? So it's the opposite of burstiness. Okay? And this is where I want to focus, because caching, natural idea of caching, will not be good for this type of processes. Okay? So what's the optimal caching policy? So let's assume that we have a cache system fed by n independent request processes with some intensities. It should say renewable here, but not renewal process yet. So a cache system or a local memory system fed by n independent request processes. Okay, and we consider the aggregate history. So this should be an n here. So we construct the filtration containing all the information up to point t of all the processes that are feeding this system. What is a causal caching policy in this setting? It should be an FT predictable stochastic process that maps the history of the process or takes values in the possible caching subsets. Okay, so it's a function or a stochastic process that says, with this history that I have seen, this should be the cache that you have to have at some point in time. Okay, this is the generalization of what I've said before for the sequential approach. So if you focus on a particular content, I, let's say I, its hit process is a point process given by, okay, it should be an arrival of type I, and it will be a hit only if this item is in the cache at the time of arrival. In that case, we have a hit. These are the green points. If it wasn't in the cache, we have a miss, and this is one of those points. Okay, but the thing is, if the policy is predictable, then this term basically is FT predictable. So you can write the stochastic intensity of this heat process, and it's just a thinning of the previous stochastic intensity. Okay, the stochastic intensity of the heat process is H for item I is just lambda I while the item is cache, and otherwise it's 0 because the item is not cache. Okay. So once you do that and you aggregate all the requests and you aggregate and consider the total heat process, the stochastic intensity, because these processes are independent, and this is important, is just the sum of all these stochastic intensities. Okay. So the thinned version of the stochastic intensities. And the steady state heat rate is just the average of this intensity process. So this is the stochastic intensity of heats. The average is the heat rate, or the average rate at which you get heats on your cache. But once you write the things in the proper way, using stochastic intensity, this is very easy to show what the optimal policy should be. If you want to maximize the heat rate, you can consider the causal policy that takes all the items puts in the cache at time t, all the items that maximize this sum. And to maximize the sum, what I have to do is take into account all the stochastic intensities of all my processes and keep the C highest. Okay? Because this will be the best we can do. So keep the C highest in stochastic intensity in your cache at every point in time, and this should be the optimal policy. Okay? So once you write the things in the proper way, the optimal causal policy becomes pretty natural to write. And in fact, there is a theorem. The first result in this regard is from Philippe Nain and Don Towsley and Giovanni Neglia, who published in 2022 a paper basically saying this. We are now trying to clean it up sometimes because it was a bit fussy on the mathematics and the definition of histories. So we are trying to put it in proper mathematical terms, but the idea was already there. Okay. So back to the Poisson case. If these are Poisson, the incoming processes are Poisson of some intensities lambda I, and we assume that these lambdas are decreasing. The total request process is also Poisson, it's a superposition of independent Poisson process. And in this case, the optimal policy is just to choose the C with highest popularity or highest intensity. So what we have here is under Poisson arrivals, white noise, statically keeping the most popular object is optimal. This was already known, okay? But it comes out naturally from this formulation, okay? So Poisson in this time-based version is like the independent reference model that I taught before in the discrete time version, okay? Because you have no local information. Everything works as white noise. Okay. So the best you can do is to keep the C most popular for all times in the cache. Can we improve upon that once we know that the system is behaving more bursty or more regularly than a Poisson process? That's the question I want to answer. Okay. So let me go now to renewal case. If you have the renewal processes of, again, decreasing intensities, intensity is popularity, so lambda 1 is the most popular, lambda 2 is the second most popular, etc. The total process is no longer renewal, but the intensity will be the sum, because on average, we will have the sum of the intensities of the incoming processes. And since the stochastic intensity only depends on the hazard rate of the process I and the time elapsed since the last arrival for process I, then I only have to keep track of the current hazard rate for each content and just to keep the C highest. That would be the optimal policy, okay, in the renewal case. So this is what the conclusion is, okay? Just keep track of the current hazard rates of the intervals elapsed and keep the C highest on your cache. For decreasing hazard rates, then caching makes sense. After an arrival, it becomes more likely to get another request. Okay, and after some time, the item has low stochastic intensity, low hazard rate, and I will evict the content from my cache, as in LRU. So this explains why LRU is a good policy for bursty traffic in this context. But what if we have increasing hazard rates? This is what was bothering me all this time. If hazard rates are increasing, when a request arrives, the item becomes less likely to be requested. So it may be better to not cache it, not to store it, and make room for other ones that are more likely. So LRU does not make sense here. Okay? If we haven't seen the request for a while, if a long time has elapsed since the last time I saw the request, then what I can do is to try to anticipate the upcoming request, because it's getting more and more likely, and try to prefetch the content in order to anticipate and serve it from the cache in time. Okay, and that's the main idea of this presentation. Okay, for increasing hazard rates, caching is not good. What we have to do is to prefetch, and this comes out naturally from this hazard rate formulation that we're presenting. Okay, so what's our main result on this? There are several results, but the main result is try to understand this optimal policy, how it behaves in the large scale scenario, so for a large system. So this optimal policy is a threshold policy. Okay, what we have to look at is at the C largest stochastic intensity. So here are the stochastic intensity of 20 objects. And what I have to do is look at I have a capacity 4, this is a small simulation. I have to look at the stochastic intensity of the 4th largest. Okay, and this will be our threshold process. If the stochastic intensity is larger than this threshold, which is random, stochastic process, then the item will be cached, otherwise it will not be cached. Okay, so I want to think about this process in large scale and what happens in steady state. And the way to think about this process is a bit difficult, but we come to some nice solutions. What I'm seeing at some point in time 0, in fact, is a random variable telling me what is the current hazard rate since the last arrival. Okay, so when it arrives, in this case it's decreasing hazard rate, the hazard rate starts to decrease, and I'm observing it at time 0. So what I have is some random variable xi of this, which is the hazard rate observed at time 0, where this time has distribution, the age distribution of the process. This should be f, not f hat. The problem is that these random variables are not identically distributed. Okay, because each item has its own popularity, each item has its own hazard rate, each item has its own inter-arrival time distribution. So I'm looking for the order statistic starting from the most popular, from the highest one, but this is the C order statistic in decreasing order of the sample, x1, x1, xn. But this sample is not, they are independent, but not identically distributed. So we cannot use Glivenko-Cantelli or some kind of law of large numbers for IAD random variables. Okay. No, there is no closed form for this. It becomes combinatorial quite fast. But can we say something about the limit? And we found this very nice theorem by Shorak that says that it's a generalization of the Glivenko-Cantelli theorem. Okay, if you have a sequence of independent random variables, not identical distribution, each one with some distribution GI, then the empirical distribution, which is the estimation of the distribution of all the random variables, we put mass 1 at each of the xi's, and we take the average, converges, if the family is tight, so under some assumptions, converges almost surely to the average of the distributions that generate the xi. So if this were IID, this average is just G0, the common distribution. But this generalizes nicely to empirical distributions and a family of non-IID random variables. Independence is important. Identically distributed, we can deal with. So we want to use the theorem to characterize the threshold. We have to put a little more structure here. We are assuming that all the inter-arrival times come from a common scale family. For instance, they are all exponential, or they are all Pareto with alpha equal 2, or they are all gamma with the same shape parameter, but different scale, okay? So in order to speed up some of the processes or slow down some of the processes and have different popularities. So F0 is our base distribution that tells how the inter-arrival times are, but we scale that distribution in order to have different lambda i's, okay? Different popularities. So in this case, we can compute the distribution of the last arrival time, or the age. We can characterize the hazard rate, and we can characterize the distribution of the random variable xi that I mentioned before, okay? So we can characterize this distribution for each incoming process, okay? And in particular, we can do it algebraically for a lot of distributions. So this can be computed exactly. It's not just an estimation or theoretical thing. This can be computed exactly, and we have some nice formulas. I've not included them here, but we have some nice formulas for some of the more interesting distributions like Pareto or airline, for instance. We also have to scale the system properly, and we also have to assume something about the popularities and how these popularities scale when the system gets large. We have a large number of, a large catalog. So N is the size of our catalog. So for these popularities, we will also define their empirical measure. This is just a way to say, okay, what's the probability of having rate lambda I if I choose one of my incoming processes at random uniformly? So this will be phi. And our assumption is that this phi converges to some probability distribution nicely. Okay, weakly is a proper term, but converges to some probability distribution. And this is in fact true for a lot of systems. I will emphasize the case of what we call the Zipf distribution, where the popularities are proportional to I to the minus beta, which is the most common distribution for popularities in caching systems. Okay, so we can put this in our framework by taking the proper scaling, and it turns out that the limit distribution is also it's a Pareto distribution related to the parameter beta that is here. And also we can see that the total arrival rate is growing, scaling up. The system is scaling up. We have more arrivals, we have more the catalog is larger, we have more arrivals coming in, the system is scaling up. So we are looking for some sort of law of large numbers here, and this is the theorem that we have. First, that this empirical distribution that I see of the samples of the different hazard rates that I sample at time 0 converges to a very nice formula for the distribution in the large scale regime. Okay, so this is the main result. What we see at time 0 converges to a proper distribution which involves the observed hazard rate distribution for the base process and the popularity distribution. It's a nice combination. It's like a convolution here. It's like a product convolution instead of sum convolution. We can talk more about it later. Okay. And the idea of the proof is just simply using that the empirical measure is near to the average, and then prove that the average under our assumptions converge to this integral. So combining everything, I won't go through the proof, but we have the main idea of the proof. Okay. So what I have characterized up to now is what's the, in the large scale limit, what is the empirical distribution of the hazard rates that I see. And what I want to characterize is the quantile of that distribution, because the quantile of that distribution tells me what is the hazard rate of the C largest popularity, stochastic intensity. Okay, so in fact, if we assume that the cache also scales linearly with the catalog, and C is a parameter which says what is the fraction of the catalog that I can store in my cache, then what I have to solve in order to compute the threshold at time 0 is to solve the empirical distribution equal to 1 minus C. So thanks to our main result, if the cache size scales linearly, we can prove a law of large numbers for the threshold. That's the main. This is a very heavily on the mathematical side. I wanted to include this because I'm very excited about these results, but maybe a bit too much for a presentation. But summarizing up to now, we can characterize via a fixed point equation via a fixed point equation what is the threshold that we should see in the large scale region. And this threshold becomes a constant, and this, under mild assumptions, this always has a positive solution. Okay? So the optimal policy becomes a fixed threshold. So in the large scale system, we only have to care about what's that threshold, not keeping up with all the hazard rates. Okay? And this is just a simulation to show that the threshold indeed happens. This is for a small catalog, 10% capacity in the local memory, some popularities, and this is small, but you already can see that the process theta of t, the real threshold, is converging to the proper solution of the equation that we computed numerically. In fact, analytically for this case. Okay. For Pareto, you can do all analytic. Of course, we are not interested in the threshold. We're interested in the performance. So what can we say about the hit rate or the hit probability of this process? Well, we have another theorem. In fact, it's easier to write it for the miss rate instead of hit rate. It's easier to deal with the miss rate that we want to minimize. And this, in fact, also converges to a proper integral that involves this threshold. It's very nice to write it in terms of expectation with respect to a variable lambda, which are the popularities, and these are distributed as phi, our limit distribution. And in fact, there's a new distribution here appearing, G tilde, which is the distribution of the hazard rate prior to an array. Okay, and I don't want to go into the mathematical details here, but the difference when I have to compute the miss rate or the hit rate is that I'm synchronizing again with the process. I have to see what the hazard rate of the process is just prior to the request in order to see if it was below or above the threshold. So what I'm interested now is in the PAM probability instead of the steady state probability again. So I have to deal with this properly. And this is why this new distribution appears. So this is pretty much our main result. So we can characterize what's the large scale behavior of the optimal policy, and this will become a threshold policy. But of course, there is more to it, because there's a connection of this threshold idea with timer-based caching policies that we analyzed before in a paper in Symmetrics 2016. And this is also an idea of Don Towsley, and we have some papers on this in queuing systems. And I would like to make the connection, because when I started studying timer-based policies a while ago, the hazard rate turns out to play an important role. And then when you go to the optimal caching policy, the hazard rate also plays a role. So what's the connection between those results? So what is a timer-based policy? A timer-based policy is upon request for an item I would check for the presence of the item in the cache. If it wasn't in the cache, like here, this is a miss, then I store the item in my cache and start a timer, ti, to evict it from the cache. If I get another request before the timer expires, I reset the timer and I keep it stored. So at some point, the requests are spaced long enough so that we have an eviction here. The item is deleted from the local memory, and we have a miss again in the next request. Okay, this is timer-based caching, and in fact, LRU can be well approximated by a timer-based policy with a constant timer for all objects. This is a very nice paper by Christine Fricker, Philippe Robert, and Jim Roberts from 2012. that explains why this works. Okay? So you can think as TTL caching as a generalization of LRU in some sense for different times. So this includes the LRU case in this setting. Of course, now we want to maximize the hit rate, so we can write the problem as assume that requests come from independent sources with intensities lambda I and some interarrival distribution fi as before. I have to choose the timers in order to maximize the hit probability subject to the occupation probability being less than C. So I'm not writing it properly here, but the main idea is this is the probability that the item is in the cache at the time before the timer expires. Okay, and this is the probability that at time 0, some random point in time, the item is stored. Okay, so this involves the PARM probability here, and this involves the steady state probability distribution here, the H distribution. Okay, and the problem is that this is a non-convex, non-linear program, but we have a very nice trick in a paper in Cuesta in 2018 with Ismael Rodriguez, a student, and Fernando Paganini. There's a proper change of variables here that make the problem convex. And you can use all the Lagrangian formulation and whatever. I will skip that in the interest of time. But the main result from that paper is if the hazard rates are increasing or even Poisson constant, the only thing you can do is to keep the most popular objects. So either the time you store the object is infinite or the time is 0. The most popular objects are there for all times. The less popular objects are just not stored. Okay. But for decreasing hazard rates, there is a threshold such that all the hazard rates at the point of at the timer point are greater than the threshold. Okay. So in fact, for decreasing hazard rates, the optimal timer-based policy is also a threshold. Okay, so this raises the question: are these two connected? I mean, we have a threshold policy for hazard rates in one sense. We have a threshold policy for hazard rates in the other sense. What's the connection? And in fact, the problem is that if the hazard rate is decreasing, waiting for the hazard rate to reach some threshold to evict the content, because to some fixed threshold to evict the content, and waiting for some time are completely equivalent. Okay? So in fact, the optimal policy for decreasing hazard rates is just a time-based policy or a threshold policy. So this is the connection between these two. And once you make this connection, you can prove very easily that for renewal processes with decreasing hazard rate, the optimal TTL policy, the optimal policy that we computed in the paper in 2018, is also asymptotically optimal within the class of all causal policies. And the key idea is to prove that the thresholds that they reach, this threshold here, is the same for the TTL policy and for the optimal, and for the law of large numbers that I showed you. Okay? So the key aspect here is TTL policies are much easier to analyze than replacement-based policies. But if they are asymptotically optimal, whatever we can say about the hit rate of the TTL policy will be a universal asymptotic bound on every caching policy that we can make. And this is very interesting. I think it's universal results like this are really interesting. Okay. And in fact, in the paper in 2018, we have an explicit expression for the hit probability for Pareto distribution. So if you have a Pareto interarrival times, for instance, and SIP popularities, we have a computable performance bound that is valid for any caching policy in the large scale unit. Okay? No policy can do better than that. Okay? But what about increasing hazard rates? I still was pondering, what if the hazard rates are increasing? Because for TTL caching, I will go back, sorry, you're storing the object. Once you see a request, you store the object. And that's not the right thing to do when you have increasing hazard rates. So once you think about the policy in terms of stochastic intensities, once you think about the policy in terms of all this nice mathematical theory of farm probabilities, the optimal policy comes out pretty nicely. What is the timer-based equivalent of the TTL policy for increasing hazard rates? So recall the behavior. Once you get an arrival for some a request for some object, the probability or the likelihood of seeing a request decreases immediately. It's less likely to see another request like this for a while. Okay. So what we should do? What should we do? And the key insight is the question now is not how long we should remember something. Sorry. You are still hearing me?
Okay. Yeah.
Okay, because
it was from another. I will check.
I have some small disconnection here. Sorry.
Okay. For me, it's okay.
Okay. So the key insight I was saying, the question now is not how long we should remember something, which is the TTL caching. Instead, is how long we should forget about something. If we forget about the item for a while and make room for other more probable items, then we are dealing with the increasing hazard rate situation properly. Okay. So what's the timer-based equivalent? It's a timer-based prefetching policy. So once I receive a request for an item, assume that it's not in the cache as before, I start a timer and say, okay, I received a request. That's great. I won't see a request for a while. So let's wait for a time t in order to get it and then prefetch it, anticipating the upcoming arrival. Of course, I may have a miss. The arrival was before the timer expired. But if we do this properly, then we may have a better hit rate than just storing the C largest popularities, which is the best TTL caching policy, as I said before. So when the hazard rates are increasing, this makes sense. Okay, and it turns out that this will be presented in a paper in MAMA workshop next month in Sigmetrics. The optimal prefetching policy has the same structure that the optimal timer policy, but with the time reverse. Okay, so now instead of f, I have 1 minus f. Instead of f hat or the h distribution, I have 1 minus f hat. Okay, but the idea is this policy can be handled almost exactly in the same manner as we handled the decreasing hazard rate case in our Sigmetrics paper. You can do the same change of variables again. You have to minimize something, you have to rewrite things properly in order to look like the previous problem. Now you are trying to minimize the miss rate over all the timers subject to some capacity constraint. This is the number of objects that I do not care about. This will be larger than an n minus c. Okay, so everything is reversed now, but the same change of variables works. And we can prove that the optimal timer-based prefetching policy for increasing hazard rate is also a threshold policy. And this threshold, again, coincides with the optimal threshold in the law of large numbers that I presented. Okay, so we have to, so the idea is the same, just with time reverse. Okay, we are waiting for the hazard rate to become high enough in order to include the system in our local network, anticipating that there will be a request in the future, in the near future. So this is another theorem in the same scaling regime for newer processes with increasing hazard rates. This timer-based prefetching policy is also asymptotically optimal within the class of all causal policies. And it's much easier to analyze and to deal with than the optimal caching policy, so LRU or whatever. So we can compute an asymptotically optimal universal performance bound for all caching policies that you may, or caching or prefetching. That's the main idea of the talk, I think. You may have caching or prefetching. It may be optimal to cache, it may be optimal to prefetch, but you can deal all these cases in a common mathematical framework that sheds some light on what the performance would be. Okay, and this is what I'm excited about, all this formulation. Just to finish with a simulation and result, because after all, I'm an engineer and I like simulations. This is an example of increasing hazard rates. Okay, so in increasing hazard rates, we can compute, this is for Erlang distribution interval time. So Erlang is more concentrated when you have the number of stages larger than 1, is more concentrated and exponential. So it's more deterministic, it's more regular. So you have increasing hazard rates. And we choose SIP popularities and vary the beta, the tail of the SIP distribution. And this is a static policy. So this is the optimal caching. And this is what you improve by using optimal timer prefetching or the optimal policy. It's just the same. This is the asymptotic bound that we compute. So there is a lot of room for improvement over caching if we do things properly. That's the main idea. And to show how bad caching may be, this is a simulation for LRU in the same set. Okay? So when the popularities are very homogeneous, are very heavy tail, this is low beta, then caching is a very, LRU or some variant of it is a very, very bad idea. Okay? Of course, if the popularities are more regular, I mean, some object is very, very popular against the other, would be this side of the curve, then all caching policies, all policies have a good hit rate because even keeping the most popular objects is also optimal in this case. So this side is more easy to deal with, but on this side, there's a lot of room for improvement over the static policy. So to conclude, I think the main result that I presented here characterizes this optimal policy that Towsley proposed in his paper, and we came to it independently, but we're trying to clean up the math because it was a bit fussy in their paper, but the key insight was there in the paper by Philippe Nain and Don Towsley. But also we characterize this policy in the large scale scenario, and it becomes a threshold policy. So this enables us to prove that TTL caching and timer-based prefetching, the timer-based versions, the things, are also asymptotically optimal and compute universal performance. The other punchline is classical caching is not well suited for regular traffic. And this is what I was concerned about with increasing hazard. And there is much more to do, so merci beaucoup. And of course, if there are any questions, I'm glad to answer.
So thank you, Andres. Any question in the room? Yeah, François.
Yeah, thank you for a very nice lecture. That's very interesting result. Can you hear me?
Yeah, a bit.
Okay.
You can talk a bit louder. That would be better.
Yeah. Okay. So I'm going to get closer to the. Okay. Yes. A couple of questions. If I got the first result, I mean, the general result is oblivious, right? Of you could have a mix of increasing failure rate, decreasing failure rate. You would still compute this max if you know the hazard rate. You compute this max, and you could mix populations of increasing failure rate, decreasing failure rate. It could be non-homogeneous in time.
Yeah,
it's completely general result, right? Of the optimal policy for.
The optimal policy, yeah. I mean, the optimal policy in a renewal case, for instance, the optimal policy is to keep the C highest hazard rates.
Hazard rates,
matter
yes,
if it's increasing or decreasing. Okay.
Okay, and so it could be a mix of increasing and decreasing.
The optimal policy would be the same. So in fact, what I'm interested in is in learning the traffic pattern. This would be
of course.
So if you learn the traffic pattern, you say, okay, for this type of people, this type of guys, they have a regular pattern. They will do one thing. And for these guys that are bursty, I will do the opposite. Okay. This would be a very interesting problem to analyze. It's more
but it is completely oblivious even of stationarity. If you were given by the gods the hazard rates, hazard rate, but the distributions, right, of the interarrivals, then you can devise a optimal policy for non-homogeneous, for the traffic, and for everything, right? So
that's a very good question. In fact, I in our main result, I assume that that we have a common base process that we are accelerating, okay? But this can be generalized, I think.
Yeah.
So you can have a combination of these, and I think that provided that we can use this Shorak result that I mentioned, the useful theorem, provided we have this convergence of empirical distributions to the average of the distributions, even if you have two classes, then the theorem will work. Okay, and you will have a law of large numbers.
Okay.
So it would be a threshold policy also. Okay.
I see. Yeah, and so my second question is that I mean there are lots of other ways of creating either repulsion or attraction, right? Cox, I mean, for instance, Markov modulated would create some sort of attraction, and therefore, I mean, more or determinantal for repulsion. And so, you have formulations for other models. So I think I mean, clustering, Cox is very natural. The Markov modulated, say, to make it. And so, do you have the same formulation for non-renewal for Markov,
okay.
Markov modulated?
Well, that's why we are trying to do the math right, because we want to precisely. I thought of this. There is some results on Markov modulated processes in Towsley paper in 2022, okay, with Philippe Nain. They use this policy with Markov modulated processes, okay, Poisson processes. So this they also try other distributions, but their main concern was about Markov modulated Poisson processes. So I started looking into this, trying to find the connection between the hazard rates itself on this, and this is why I went through this path. But of course, there is a lot more to do. I think Markov modulated Poisson processes may be another way of thinking about this problem. The intensities will be more like more manageable in that case, because stochastic intensity of Markov modulated Poisson processes are easy to compute. So in fact, what you have to determine is whether you are in the on or off phase of the Markov modulated Poisson process, if I'm right. So I think we can use all this framework to get this type of results also for this type of processes. If you want to see some numerical results on that, you can go to the paper by Towsley and Philippe Nain that precisely try with this distribution. But the thing is, for non-renewal, you won't have this hazard rate problem. Okay, so I'm concentrating on the hazard rate here, because the hazard rate is what appears in the TTL caching problem. So the optimal policy will depend on the hazard rate. Completely optimal, the absolute optimal policy will depend on the hazard rate only in the renewal case. If you have more information in the history of the process, then it will not depend only on the hazard rate of the current window, and that's key. Okay, and this is one of the things that we wanted to differentiate from Towsley's result. Okay, because in Towsley's result they write everything in terms of any history or whatever, but what is the information that I have? That's important. If the process is renewal, I know that every arrival will change, will reset all the previous information. And so I have to think about Markov modulated Poisson processes, but it's a very nice question. Thanks.
Thank you.
Other question in the room? Question on the bridge? So thank you again, Andres.
No, thank you.